Imagine a place where sunlight has never touched. A realm of perpetual night, where the crushing weight of the world presses down with unimaginable force. This is not some distant planet, but a part of our own Earth, hidden just beneath the surface of the familiar ocean. It is the most solitary, the most extreme, and perhaps the most mysterious environment on our blue marble. What secrets does it hold? What life, if any, could possibly endure such impossible conditions? We journey now to the very edge of human understanding, into the deep. Our destination lies within the vast expanse of the Pacific Ocean, a crescent-shaped scar known as the Mariana Trench. And at its very bottom, a chasm within a chasm, is the Challenger Deep. It is the deepest known point in all of Earth's oceans. A name that evokes both challenge and an ultimate boundary. For centuries, its existence was largely theoretical, its true nature shrouded in the impossible depths. A place that defies our conventional understanding of what constitutes a habitable environment. But what exactly defines this ultimate abyss? To grasp the sheer scale of the Challenger Deep, consider its staggering depth. From the ocean surface, one must descend approximately 10,935 meters. That's nearly 11 kilometers straight down. If Mount Everest, the tallest peak on Earth, were placed at its bottom, its summit would still be submerged by more than 2 kilometers of water. It's not merely a deep spot, it's an entirely different world, vertically inverted, existing in a dimension almost incomprehensible to those living on the sunlit surface. A scale that forces a complete recalibration of perspective. This immense vertical distance translates into an equally immense pressure. At the bottom of the Challenger Deep, the weight of the overlying water creates a force of over 1,000 times atmospheric pressure at sea level. To visualize this, imagine 50 fully loaded jumbo jets piled directly on top of you, their combined mass compacting every inch of your being. It's a force that would instantly crush most known life forms, pulverize steel, and compress almost any structure designed for surface living. How could anything possibly withstand such an extreme, constant, and unyielding embrace? And then there is the cold. In this lightless abyss, temperatures hover near freezing, typically ranging from 1 to 4 degrees Celsius. Such extreme cold slows metabolic processes, freezes biological structures, and challenges the very chemistry of life. It's a persistent, biting chill that never relents, compounded by the lack of any significant warmth from the sun. Organisms on the surface struggle to survive even short exposures to such temperatures. Yet, at these depths, it is the constant, the baseline for existence. A frigid, crushing, and absolutely dark world. Perhaps the most defining characteristic of the deep sea is the absolute absence of sunlight. Below a certain depth, the sun's rays simply cannot penetrate. This creates a realm of eternal darkness, a void where photosynthesis, the engine of most surface life, is utterly impossible. No plants, no algae, no primary producers as we understand them. The entire food web, therefore, must operate under fundamentally different rules. How does life draw energy in a world without light? Where does the very foundation of existence come from when the sun offers no warmth, no energy, no hope? Picture the seafloor here, an expanse of fine, silty sediment, accumulated over millennia, stretching into an endless, inky blackness. Geologically, it's a dynamic zone, shaped by tectonic forces, yet visually, it appears static, silent, and desolate. No vibrant coral reefs, no swaying kelp forests. Just the subtle undulations of a seabed where time seems to slow, where changes are measured in geological epochs rather than seasons. It is a landscape that feels utterly alien, divorced from any terrestrial experience. But even here, life has found a way. A tenacious, specialized, and often bizarre way. For a long time, the prevailing scientific consensus held that life simply could not exist in such an extreme environment. The crushing pressure, the biting cold, the absolute lack of light, these factors seemed insurmountable. Scientists believed the deep ocean was an abiotic zone, a sterile void. It was an understandable assumption, given the constraints. How could complex biological systems function when even molecules are strained by pressure and energy is non-existent? The very thought of thriving life here seemed to contradict fundamental principles of biology. But nature, as always, had other plans. The first hints of deep-sea life began to emerge not from direct observation, but from indirect evidence. Strange organisms occasionally tangled in fishing nets, or found washed ashore, bearing marks of pressures far greater than coastal waters. Then, the discovery of hydrothermal vents in the 1970s revealed entire ecosystems thriving on chemical energy. It was a paradigm shift. Life, it turned out, was far more resilient and adaptable than we had ever dared to imagine. The deep was not sterile. It was teeming. But what kind of life, precisely, could defy every known rule? With sunlight utterly absent, the conventional energy source for life, photosynthesis, is impossible. So, how do these deep-sea ecosystems function? The answer lies in a process called chemosynthesis. Instead of light, these organisms harness energy from chemical reactions, primarily utilizing compounds like hydrogen sulfide expelled from volcanic vents or methane seeps. It's a completely different foundational principle, creating independent oases of life far removed from the sun's influence. This revelation wasn't just about the deep sea, it expanded our understanding of life's potential, even for astrobiology. At the base of many deep-sea ecosystems are the microbes. Tiny, single-celled organisms, but immensely powerful. These extremophiles are masters of survival, thriving in conditions that would obliterate most other life. Some derive energy through chemosynthesis, forming the very foundation of the food web. Others specialize in breaking down organic matter that drifts down from above, marine snow. They are the invisible architects, the tireless recyclers, making life possible for everything else. Without them, the deep would truly be barren. Their existence redefines the boundaries of biological endurance. The term extremophile was coined for organisms like these, life forms that thrive in environments once considered utterly hostile. High pressure, extreme cold, absolute darkness, toxic chemicals, these aren't just conditions to be endured, but conditions to be exploited. Their biochemistry is fundamentally different, their cellular structures uniquely adapted. They represent the ultimate survivors, pushing the boundaries of what we thought biological life could tolerate. Each discovery in the deep sea adds another chapter to this incredible story of adaptation, reminding us that life's tenacity knows few bounds. What other marvels await? But beyond the microbial world, could more complex life exist? Small, mobile creatures that scavenge or hunt in the perpetual night? The early explorations, using rudimentary deep-sea cameras and dredges, hinted at movement. Fleeting glimpses, strange forms captured in the abyssal gloom. These were the first tangible proofs that multicellular organisms had also mastered this realm. Not just static colonies, but active, living beings navigating the crushing cold and darkness. What might these creatures look like? How could they possibly move, feed, and reproduce under such an extraordinary burden? Among the most common and crucial creatures of the deep are the amphipods. These small, shrimp-like crustaceans are the relentless scavengers of the abyss. Descending through the water column, they rapidly locate and consume any organic material that drifts down, decaying fish, marine snow, even the carcasses of whales. They play a vital role in recycling nutrients, preventing the seafloor from becoming choked with debris. Their sheer numbers and efficiency demonstrate an astonishing adaptability. How do these seemingly fragile creatures withstand such immense pressure, yet remain agile and voracious? The secret to surviving extreme pressure often lies in an organism's physical composition. Many deep-sea creatures, including amphipods, possess highly flexible, even gelatinous bodies. Their bones, if present, are often remarkably soft and pliable, preventing them from shattering under the immense force. Their bodies are mostly water, a substance that is largely incompressible. They lack gas-filled organs like swim bladders, which would simply collapse. This elegant solution allows them to exist as if the pressure doesn't truly register, their very biology aligned with the crushing environment. A fundamental reimagining of skeletal structure. Another marvel of the deep are the xenophyophores. These aren't just any single-celled organisms, some can grow up to 10 centimeters across, making them giant amoebas. They construct elaborate, delicate shells from sediment particles, forming intricate structures on the seafloor. They are filter feeders, gently sifting through the water for microscopic detritus. Their size and complexity for a single-celled organism challenge our assumptions about cellular limits. These elegant, fragile giants persist in an environment of crushing force, a testament to the diverse strategies life employs. They are truly living architects of the abyss. In 2017, a remarkable discovery cemented the fact that even fish, with their more complex organ systems, could thrive at extreme depths. The Mariana snailfish, or Pseudoliparus swirii, was identified as the deepest dwelling fish known. It lives at pressures up to 8,000 meters, far exceeding what scientists once thought possible for fish. Its existence immediately posed new questions about the biological limits of vertebrates. How could a fish maintain its internal structure, its organs, its very life, in a place that should render it instantly lifeless? The answer lies in its unique physiology. The Mariana snailfish is perfectly engineered for its environment. Its body is largely composed of a gel-like substance, helping it to maintain buoyancy without a gas-filled swim bladder. Its bones are extremely flexible, preventing them from cracking under pressure. Its tissues contain high concentrations of trimethylamine N-oxide, TMAO, a chemical compound that stabilizes proteins and prevents them from denaturing under extreme conditions. It's a living example of elegant biological design, where every aspect of its being is a direct response to the immense forces of its home. A marvel of evolutionary adaptation. Another resident of the deep, equally adapted yet strikingly different, is the gummy squirrel, or Psychropotes longicauda. This isn't a land creature, but a type of sea cucumber, distinct for its translucent, gelatinous body. It moves slowly, almost ethereally, across the abyssal seafloor, using small tube feet. Its diet consists of detritus, the organic fallout from the layers above, which it sifts from the sediment. Its slow, deliberate movements and soft, vulnerable appearance belie its incredible resilience. A gentle giant of the deep, existing in a realm that would be instantly fatal to most. A testament to nature's diversity. In a world devoid of sunlight, many deep-sea creatures have evolved their own light source, bioluminescence. This chemical light is used for myriad purposes, attracting mates, luring prey, startling predators, or even camouflage through counter-illumination. It creates a breathtaking, alien light show in the eternal dark, turning the abyss into a canvas of flashing, glowing forms. From simple glows to complex patterns, bioluminescence is not just a spectacle, it's a fundamental language of survival in the deep, a silent conversation in the vast blackness. What are they truly saying with these ephemeral lights? Among the most enchanting creatures of the deep is the Dumbo octopus, Grimpoteuthis. Named for the prominent, ear-like fins on its head that resemble Disney's famous elephant, these octopuses drift gracefully through the water column at depths of 3,000 to 4,000 meters. They use their ear-like fins for propulsion, gently flapping them to glide, while their arm webs help with steering. Their ethereal movements and unique appearance make them seem like something out of a fantasy. Yet, they are very real, a testament to the diverse and often whimsical forms life can take in the most extreme environments. A delicate ballet in the crushing dark. The Dumbo octopus's method of locomotion is particularly fascinating. Instead of the jet propulsion typical of many cephalopods, Grimpoteuthis primarily relies on its large, wing-like fins. This adaptation allows for slow, energy-efficient movement through the dense, cold water, preserving precious energy in an environment where resources are scarce. Its arms, connected by a web, also aid in steering and occasionally capturing prey. It's an elegant solution to deep-sea living, demonstrating how evolution can craft completely different strategies for similar challenges, creating beauty and efficiency in the most unlikely of places. A silent, graceful flight. Despite the extreme conditions, the human spirit of exploration has always been drawn to the unknown, to the final frontiers. The deep sea, in particular, has captivated imaginations for centuries. What drives us to descend into such hostile, alien worlds? Is it pure scientific curiosity, the allure of discovery, or something more fundamental, a primal urge to push boundaries and understand our place in the universe? Whatever the motivation, the journey to the Challenger Deep represents one of humanity's most ambitious and dangerous quests, requiring extraordinary courage and ingenuity. How did we even begin to approach such a place? The first manned descent to the Challenger Deep was a monumental achievement in human history. In 1960, the Bathyscaphe Trieste, an extraordinary submersible designed for extreme depths, embarked on this perilous journey. A small, spherical pressure hull, barely large enough for 2 men, suspended beneath a giant gasoline-filled float, gasoline, being lighter than water, provided buoyancy. It was a daring design, fraught with unknowns, pushing the limits of materials and engineering. The world watched, holding its breath, as 2 men prepared to plunge into the greatest abyss on Earth. A truly pioneering mission. On January 23, 1960, 2 brave men, Swiss oceanographer Jacques Picard and U.S. Navy Lieutenant Don Walsh, made history. They successfully piloted the Trieste to the bottom of the Challenger Deep. After a descent lasting nearly 5 hours, they spent a mere 20 minutes on the seafloor, observing life through a tiny viewport. What they saw was not the barren wasteland many expected, but the subtle movement of a small flatfish and a shrimp. Their brief observations shattered long-held beliefs, proving that complex life could indeed exist. A testament to human courage and scientific perseverance. Over half a century later, a new generation of explorers sought to revisit and further investigate the Challenger Deep. In 2012, filmmaker and explorer James Cameron, known for his epic movies, embarked on a solo mission in his purpose-built submersible, the Deep-Sea Challenger. This sleek, vertical torpedo-like vessel was designed with advanced materials and technologies, allowing Cameron to maneuver and film in 3D, bringing the abyss to life for a global audience. It marked a significant leap in deep-sea exploration, blending cutting-edge science with the art of storytelling. James Cameron's Deep-Sea Challenger mission wasn't just about reaching the bottom, it was about scientific data collection and cinematic immersion. He spent hours on the seafloor, collecting samples of rocks and organisms, and capturing unprecedented 3D footage. His journey provided invaluable data for marine biologists and geologists, revealing the subtle movements of abyssal creatures and the stark beauty of the deep. Cameron's unique blend of scientific ambition and storytelling prowess brought the remote, alien world of the Challenger Deep into sharp focus for millions, inspiring a new generation of oceanographers. The latest chapter in human deep-sea exploration belongs to Victor Vescovo and his remarkable submersible, the DSV Limiting Factor. Launched in 2019, this vessel represented a new paradigm in full ocean depth technology, capable of repeated descents to the deepest parts of the ocean. Unlike its predecessors, Limiting Factor was designed for multiple dives and robust scientific operations. Vescovo's ambition was not merely to reach the deepest point once, but to systematically map and explore every one of the world's 5 deepest ocean trenches. A new era of accessibility to the extreme depths. Victor Vescovo, an American explorer and businessman, achieved an unprecedented feat. He became the first person to visit the deepest points of all 5 oceans, a journey known as the 5 Deeps Expedition. Using the DSV Limiting Factor, he completed multiple descents to the Challenger Deep, setting new records for manned dives. His missions yielded vast amounts of new data, including high-resolution sonar mapping of the trench and the collection of numerous biological samples, further expanding our understanding of these mysterious environments. He didn't just visit, he charted a course for future discovery. The construction of submersibles capable of reaching such depths is an incredible feat of engineering. Their pressure hulls must be meticulously designed and built from specialized materials, often titanium, to withstand the immense forces. Redundancy in life support, navigation, and communication systems is critical. Every component, from a simple bolt to complex electronics, must function flawlessly under conditions that would crush standard equipment. It's a testament to human ingenuity, pushing the very boundaries of material science and mechanical design to create a vessel capable of protecting human life in the most hostile environment on Earth. Each descent is a triumph of engineering. Beyond the crushing pressure, explorers face a litany of other challenges. The near-freezing temperatures stress mechanical systems and require precise thermal regulation within the submersibles. The absolute darkness necessitates powerful, yet compact, lighting systems. Communication with the surface is often delayed or impossible due to the sheer distance and water density. Navigation without GPS or visual cues is extraordinarily difficult, relying on advanced sonar and inertial systems. Each dive is a dance with the extreme, a calculated risk against the overwhelming forces of nature. Every element must be meticulously planned and executed. The technology developed for deep-sea exploration has far-reaching implications beyond the oceans. Advances in pressure-resistant materials, remotely operated vehicles, ROVs, autonomous underwater vehicles, AUVs, and sophisticated sensor technologies are applicable to space exploration, medical devices, and other extreme environments. The deep sea serves as a crucible for innovation, pushing engineering and scientific boundaries in ways that benefit us all. It is a technological frontier, constantly expanding what is possible, not just for diving, but for discovery across all scientific disciplines. The lessons learned here echo far beyond the abyss. But why does humanity continue to invest so much effort, risk, and resource into studying a place so remote and seemingly inhospitable? The answers are profound. The deep sea holds clues to the very origins of life on Earth. Its unique ecosystems and extremophiles offer insights into biological processes that could lead to breakthroughs in medicine and biotechnology. Understanding deep-sea geology helps us comprehend plate tectonics and seismic activity. It is a vast, interconnected system that influences global climate. To truly understand our planet, we must first understand its deepest, darkest secrets. What else waits in the gloom? The extremophiles of the deep sea are a potential goldmine for biotechnology and medicine. Enzymes that function at high temperatures and pressures, or in the presence of toxic chemicals, could revolutionize industrial processes, drug development, and even waste treatment. Imagine bacteria that can break down plastics in extreme conditions, or compounds that offer new avenues for antibiotics. These organisms have evolved unique biochemical pathways for survival that are entirely novel to science, waiting to be discovered and harnessed. The solutions to some of humanity's biggest challenges might lie dormant in the abyss. The deep sea plays a critical, yet often unseen, role in regulating Earth's climate. It acts as a massive carbon sink, absorbing significant amounts of atmospheric carbon dioxide over geological timescales. Deep ocean currents distribute heat and nutrients globally. However, these delicate ecosystems are not immune to the impacts of human activity. Plastic pollution reaches the deepest trenches, and changes in ocean chemistry, such as acidification, could have profound and irreversible effects. Studying the deep allows us to monitor these changes and understand their global repercussions. The health of the abyss is connected to the health of us all. Despite decades of exploration and groundbreaking discoveries, the vast majority of the deep sea remains unseen, unstudied, and utterly unknown. We have explored less than 5% of our oceans. Each dive, each new sample, each flickering image from a camera, only deepens the mystery. What other creatures, what other adaptations, what other biochemical marvels await discovery in the crushing dark? The Challenger Deep, while explored, represents only one tiny window into this immense, hidden world. The questions far outnumber the answers, fueling an endless curiosity. The abyss still guards its greatest secrets. The deep sea, though seemingly alien and remote, is intricately connected to every aspect of our planet's life support systems. From the air we breathe to the climate that sustains us, the health of the abyss resonates globally. The creatures found there challenge our preconceived notions of life, inspiring awe and a deeper respect for nature's boundless creativity. As technology advances, our ability to explore and understand this hidden world will only grow. What we find there, what we learn about resilience and adaptation, will undoubtedly shape our future, reminding us that even in the most solitary place on Earth, life finds a way. And its story is far from over.